So let me introduce everyone to this session on using new forms of data to analysing cycling activity. Dr. Jin Hong is a senior lecturer on transportation planning and urban studies and leads on the transport and infrastructure team at UBDC. Jin's research interests include interaction amongst the built environment, travel behaviour and air quality, transportation and planning, the built environment, safety and walking, and travel survey techniques. I see we have participants from Australia, Austria, Belgium, China, Germany, Iraq, the Philippines, Russia, Turkey, Ukraine, and the UK. Sorry if I've missed any of you. As you will have seen, this session is recorded and will be uploaded in the web in an accessible format at some point after the session. Details will be provided on the UBDC website. Also, check out the website for other resources, including how to access other data and other training and events delivered by the UBDC. As we've mentioned, cameras will be turned off and microphones muted to aid privacy and also for bandwidth reasons. Please use the Q&A facility to ask questions. These will be collated and responses will be provided in the Q&A sessions. In terms of the session structure, Jin will give a presentation for around 30 minutes, which will be followed by a Q&A session of 10 to 15 minutes. We will then have a break between sessions for 15 minutes or so, and then we will have our second session with a similar format, 30 minutes presentation, and again, 10 to 15 minutes for questions and answers. So I'd just like to introduce our presenter, Jin Hong, and I'll hand over to Jin.
Thanks a lot, Moore, and thanks for all of you to join today's webinar, and I'm sorry for the delay. In this session, as Moore said, I will talk about cloud source cycling data, and as a researcher, that is Strava data, and as a researcher, how we have used the data for cycling studies. In the next session, I will do some kind of tutorial, as you may know. So, I think, yeah. Here's a brief background about the study. So the large benefits of the cycling have been well documented. It could reduce the auto dependency, therefore reduce the level of congestions and emissions. It could also improve the public health because people are doing physical exercise while cycling. In addition, if you look at the travel surveys from different countries, you will notice that a substantial amount of the automobile trips are short trips. That means their travel distance is between 2 kilometers and 5 kilometers. What does that mean? This is quite long distance for walking. However, this is a really reasonable distance, travel distance for cycling. So it implies that cycling can be a good alternative of the automobile. So because of this huge benefit and the potential, many countries have used their substantial resources to improve the cycling environment and also increase cycling. And this is the same for UK. The active travel, walking and cycling is one of the priorities for the national transport strategies in the UK. In Scotland, we have really ambitious vision. Transport Scotland wants 10% of journeys to be made by bicycle by 2020. This is really ambitious because now we have 1 to 3% at most. And then cities are responsible for achieving this. So again, we are trying to promote cycling. Glasgow, the local government have also introduced several measures and interventions to promote cycling. For example, they want to use 2014 Commonwealth Games. This is the sports game, international sports game, as a catalyst to promote cycling, to increase the cycling. So they provided several cycling infrastructure lanes before, during, and after the Commonwealth Games. In addition, they also provide bike share program, Next Bike, as you can see in the pictures. They are quite popular at this moment. However, as a planner, if you want to make better cycling plans, you really need to understand the cycling pattern, cycling behavior. And also you need to understand how to use the proper data to evaluate the effectiveness of interventions. Unfortunately, these are very difficult because we don't have a proper data. We have travel survey. So many people actually use travel survey to examine travel behavior. However, there are only small number of cyclists in most cities. And then although it's representative sample, the travel survey, they only include a small portion of the people from the population compared to the population. So what happens is at the end, you may end up with 40 or 50 people who cycled in your travel survey for a metropolitan area. Then that's too small. You cannot really use that data to build some model or to analyze detailed cycling activities. We also have a manual and automatic count. So for example, in Glasgow, every year for 2 days, they manually count how many cycles in and from the city center. And some cities, they installed the automatic counters to continuously measure the cycling activities. Again, these are very expensive, hence infrequent. There are only a small number of automatic counters in the city because again, it's very expensive. So it's really good ground truth data, they are, but there are significant limitations if we want to use this data to examine the cycling patterns, cycling behavior. Due to the technology improvement, now we have new forms of data. And these data provide detailed cycling activities at the fine, spatial, and temporal scale. The Strava cycling app is one of them, and I think it's one of the most popular cycling app in the world. And they use GPS to track cyclist journeys. So they know exactly what time and where the Strava users are using cycled. So that is a really amazing data set. And as time passes, more people are using this app because it became popular. So then what does that mean? The quality of the data will be improved because there are more data. In addition, the data are already being collected all over the world because that's everyone can download the apps. So we can compare the different the same policy in different countries using the same data format. And we also can use the same approach, methodological approaches to different cases because the data structures are exactly the same. However, as a researcher, we really need to understand then what could be the potential weaknesses of these emerging forms of data, which could influence our study. So what are the weaknesses? The first thing is representativeness. I guess you already know this one. For example, in Strava case, it's more likely young male people are more likely to use the Strava apps. And they are more experienced cyclists than the normal cyclists. So if their cycling patterns are different from those of the normal cyclists, then what? The result, the analysis could be biased. So we could get incorrect conclusions. So there are many people recently who have tried to employ the advanced analytics methods to correct the bias. There are also special variation. As I said, most cities have only small number of cyclists. And among them, only small number of people actually use the Strava apps. So if you look at the popular roads, you may find some people who use the Strava apps. But if you look at the less popular roads, although there are actual cyclists, you may not have any Strava users. So it depends on where the place is. Some people argue that Strava data is more useful for urban area where the level of cycling activities is high compared to the rural area. Lack of social demographic information. mainly because of privacy issue. We all know that the social demographic factors are very important determinants of the travel behavior, like age, gender, income, education level, and so on. However, we don't have that information. The last one that I want to talk about is a regulation from the company. This is actually very important, and I will talk about the Strava case later. Because the data is owned by the private company, if they somehow change their regulation or their product because of privacy or to protect their app users, this is beyond our control. We cannot really request their decision against their decision. So we just need to accept it, and they could influence our whole study or the methodologies that we have used before. And this can be another problem in the near future, because now a lot of private companies, they collect their own data. There are also others. Then what are the strengths? I already mentioned several things. It's the most up-to-date information. Right now, they are also collecting the data because several people are using the Strava apps. It's cost saving. They don't really pay anything. And it's very detailed cycling activity at the fine, spatial, and temporal scales. And again, growing number of users. So that could improve the quality of the data. So this was the brief introduction about the cycling studies and also Strava. Here, I want to introduce 3 published papers that use the Strava data from our side. And I hope this will give you some kind of idea about how we use the data. And these are the 3 research questions that we aim to answer. The first one is, can crowdsourced cycling data be utilized for cycling behavior studies? This is about the quality of the data, whether the data, Strava data, are good enough for studying the cycling activities. The second one is, if yes, then where commuting cyclists traveled and what are the influential factors for their route choice? Because we have such a detailed cycling activities in the whole city area. The last one is, do the new cycling infrastructure investment in Glasgow produce effective impact? So these are the 3 research questions that I'm gonna introduce. So what data and variables? We used a multi-years of Strava data, 4 years of Strava data, 2013, 14, 15, and 16. By the way, these data are available in EBDC. You can get the data based on your request. Data used to be provided as origin and destination with route information at the output area level. Output area is a UK census area. It's pretty small. So what it means is we know for each trip where the trip starts, output area, and what output area the person traveled, and where is the destination, output area. This is pretty nice data. Second one is a more detailed one. Minute by minute link count, or link count, edge count is the kind of road segment. At the road segment, we know how many people cycled on a particular time, and minute by minute. This is really detailed data. We also have information about waiting times at junctions, and then aggregated demographic information, for example, age and gender for your city. They just give you aggregated summary. Now, they changed the product because of the privacy issues. From 2018, Strava Metro, the company, has provided binned count data. So what does that mean? They aggregated cycling counts in 5 count buckets. For example, if counts are less than 3 or equal to 3, it becomes 0. If counts are between 4 and 7, it becomes 5. What's the implication? As I said, there are a small number of cyclists, and among them, small number of people are using the apps. So what it means is if you look at the whole city, it's fine for daily or hourly data, you will see a lot of majority of the roads, they will only have 1, 2, 3 or 0 Strava users. So one, depends on the cities, one Strava user could represent 25 to 100 actual cyclists. And because they are bringing this data, they just lose the huge information. So that could influence your level of aggregation, your analysis unit. Now, they only provide hourly aggregation is the lowest level of aggregation, not a minute by minute. I think it's because of that issues. So that is a big issue. Again, if that happens again, the whole methodologies we have used before may not be available because some methods, they use the more detailed, like, temporal scale. So we used the 4 years of the Strava data, but at the time, the unbinned data was available. So we used unbinned data for our own study. We also use a manual count of cyclists from Corden Count carried out in Glasgow in the same time period. So there are 38 locations and 2 days in general in September per year. I will show you the location later. And we also use Glasgow cycling infrastructure data, as you can see on the map. That is the current infrastructure map. And then this is a river. And we see there are really good, nice cycling infrastructure alongside the river and here and other parts. So we can see some area like this one, east side of the Glasgow, where it's the most deprived area. There are not many good cycling infrastructure. So we can see some kind of special inequality issue here. So for the research question 1, about the quality of the data, how can we check the quality? We can check the ground truth data, which is a manual count data with Strava data. So in the map, you can see the 38 location, and that's the location where people check the number of cyclists. And we know the location and time of the number of actual cyclists. And we know exact time and same location from the Strava data. So we compare them. That's how we do that. So there are 2 types of analysis. One is a correlation analysis, and the other one is simple linear regression model. The equation shows the simple linear regression model. Yi means represent the number of cyclists from the Corden count, so ground truth data, and X Strava means number of Strava cycling trips with simple linear regression model. And for this analysis, we use time period, 3 time period. What it means is we aggregate the count for AM peak, afternoon, and PM peak. The reason is we found later, if we aggregate that level, we could have the data quality could improve much better, right? So the total sample size is 684 because we have 38 location, 3 time period, and 2 days and 3 years. That is for the first research question. So for the second research question, we use the 2016 Strava data, but OD metrics. We can construct OD metrics because we know the output area of the origin and destination for each trip. So we compare the routes taken by commuting cyclists, that means the Strava data, raw Strava data, with the route they would take if they minimize their travel distance. So how can we do that? We use the traffic assignment model and then estimate based on the same OD metrics, the shortest travel distance path, and then find out the traffic volume per each link edge. And we compare them. And we also use Google Maps and local knowledge to figure out why some roads are popular, why some roads are unpopular, less popular. For the research question 3, we use the 4 years of Strava data, and we calculate the total number of Strava trips per output level per month. It's monthly total. Why? As I will show you later, as we increase the level of aggregation, the data quality becomes much better. So monthly average, we think it's really good enough for this study. We used output area as an analytical unit. Then we use the fixed effect Poisson panel regression model as you shown in the equation. So the dependent variable is number of cycling trips in area I, output area I in month T. This is the 4 years of data. So panel data. And we have 4 infrastructure you can see on the map. And then this one is interesting because the longest one connects the suburban area to the city center. Here is the city center. Here. So this is the result for the research question 1, correlation analysis and simple linear regression model. We have different levels of aggregation because we think if we aggregate more and more, the data become larger and large. We will have more counts, so we may have a better kind of result. So the lowest level of aggregation is hourly, and the largest one is the 2 days, because we only have 2 days of codon count data. And correlation, even hourly, we find 0.78, almost 0.8. This is very high. It gives us positive signal. For the 2 days of aggregation, we have almost 0.9, which is really good kind of indicator. When we look at the linear regression model result, the estimates for the Strava trips variable, our independent variable, is positive and very significant. And the adjusted R-square is 0.74. By using this one variable, this simple linear regression model can explain the 74% of the variations in the codon count data. That is a huge one. So these 2 results gives us kind of positive signal. Yes, Strava data could be used to examine the spatial variation of the cycling patterns. The full graph shows the relationship between Strava data and the codon count. The x-axis is Strava data, number of Strava data. Y-axis is number of codon count. As you can see, hourly aggregation, there are a lot of noise at the bottom part, left bottom, because again, there are only small number of people who cycled. But if we aggregate, we see a more clear pattern of the linear regression and noise becomes smaller. So based on this result, we concluded that yes, it could be a good good proper data for cycling studies. For the second research question, we compare the short routes and actual routes. The graph on your left panel is actual Strava data. So that's where people really cycled. So we see alongside the river, there are some concentration. They are popular and makes sense because amenity is one of the main factors and for cycling, and also safe cycling lane infrastructure. For the shortest path, you see more evenly distributed kind of patterns. And that also makes sense, but it's already hard to see. So to make better vision, we calculate the difference between them. Here, the red means it's more popular. So there are more cyclists, so cycling trip happen on these roads compared to predicted one. And the black means they are unpopular, less popular. And the thickness means the difference, size of difference. So we see alongside the river where there are good cycling infrastructure, there are really many people cycle. But around the city center area, there are some red lines and black lines, but they are very thin. It means their difference doesn't really that different. That totally makes sense, right? So then we see, based on our local knowledge, want to figure out why some roads are less popular. And here's one example. This is the one from the downside of the city center. And other roads are very popular, but this road, although it's very straightforward, it's straight lanes, it's not really, it's less popular. And see, through the Google map, we want to see what's the problems. And these are the 2 pictures. we can see the bus stops, traffic lights with the pedestrian crossing, and street parking. See this, there are a lot of street parking and these cars there, and no cycling infrastructure. Those are the factors often mentioned in the previous studies, empirical studies, as the barriers of the cycling. So we see, yeah, maybe that's a reason. The another one, this is the east part of the Glasgow, and actually there is a cycling lanes, however, shared with bus. And you can see a lot of car park, and also the built environment. This area is one of the most deprived area, high crime rate, the safety issue. Again, these are often mentioned as barriers for cycling. And we can find those kinds of potential factors. So when we did this analysis, we think this would be really good and simple tools for planners. They can really easily see where are the popular roads, where are the less popular roads, and what are the potential regions. They can understand their cities better. For the research question 3, we use the model, and these are the four investment. And we remove the time trend and then see how the total monthly count change. And the line here you see the different line, location of the line. That's the when the new infrastructure will open to the public, right? And we see the 3 of them has pretty positive increase after the new infrastructure were opened. However, this one, the route to Caskin 1, which actually connect the city center to the suburban area, the longest one, has kind of negative trend. So after these basic stats, we jump into the model, and then these are the results from our model. We first measure the overall effects, and you can see there is a positive impact, and it's about 8% increase. You have to take an exponential to interpret the result, but the p-value is 0.08, which is greater than 0.05, so it's not really statistically significant. However, if you examine the separate effects, we notice that 3 among 4 have very positive impacts, and they are very significant. It means 12% to 18% increase after new infrastructure were introduced. And the route one, the first one, Caskin 1, it has a negative kind of impact compared to the other upper area where there's no new infrastructure. So that is a reason why we didn't really get the significant result for the overall effect. So, and these the 3 new infrastructure, they are close to the city center area, and they include the segregated lanes. So they could provide some kind of policy implication. If we want to get a short-term impacts, then better to build more cycling lanes, maybe near the city center where the level of cycling activities is high, and also the segregated lanes could be important. So this is the end of the slide. If you want to look at more in detail about each studies and methodologies, you can look at these 3 papers. They are open access, so you can download for free. And this slide will be available for you, so you can get the whole information. Thank you very much.
Thank you very much, Jin. We have some questions here. If I read them out one by one, Jin, you could maybe try and answer them.
Yep.
So the first question is, and I think you touched on this, how much Strava use the apps for commuting rather than the kind of Lycra warriors that we see racing about the city that you mentioned? How many are kind of normal commuters, if you like?
I think, so in our case, it was almost 5% of people are among the whole cyclists, 5% of the people are using the Strava apps. And then, yeah, that's for our city, but it depends on the city by city.
Okay, thanks for that. Now, probably there might be some answer in the links you gave for your papers. In terms of cycling research case studies, a journal, and is a transport planning or something, any of the kind of common journals that you tend to publish in, Jin?
Yeah, so we published several papers in several leading transport journals: Transport Geography, Transportation, and then Environment Planning B. So and also we published some paper in Transport Research Part A, which is a top transport journal. So you can find more information on my website or on UBDC website.
That's great, thanks, Jin. Now, the next one, have you tried to identify trips in cycling mode from other mobile phone data, for example, Telefonica or Voda UK instead of Strava?
No, actually, we haven't, because we are trying to get some mobile phone data. Urban Big Data Center, we try to buy some mobile phone data. Then we could do it. That is actually in the next step that we want to do, because we want to also look at the other data sources. So currently, we are planning to buy some mobile phone data, and we will also plan to conduct a survey with the apps. So we can check the people's location and their trips. So then we can use this data to detect mode choice from the mobile phone data. So we hope we can have another session later using these new forms of data.
Good stuff. Now, another question here specifically about somebody who maybe knows Glasgow. In terms of popularity of routes for cycling, was consideration given to the physical and environmental factors, e.g. topography or gradient? I think what they're meaning is, in Glasgow, some of the streets have very big, long hills on them. Did people make a decision? Did you see any of that, Jin, where people took a route because it was an easier cycle?
Yes. So I will show you in the tutorial. Actually, I will show you how to produce the maps using the Strava data, and you can see majority of the activity happens alongside the river, which is very nice infrastructures will provide and very flat. And then you will see some kinds of less popular roads in some area, very hilly areas. So you can see, you can easily examine that kinds of patterns by using Strava data for your own city.
Good stuff. Now, one, I'm not sure how much detail we'll provide here. May I ask how much Strava charged for the data, and what is the attitude of people in Strava towards research projects, or are they very commercial focused?
Yeah, this is one that we may ask to Andrew, who is the administrator majors in UBDC, senior major. I think we somehow spent 60K to buy the data for Glasgow area for several years, but that's depends on the license, because as you see, we purchase the data, and so everyone who wants the Strava data, they can request and then get it for free. So if you are interested in the Strava data for Scotland, especially, you can get the whole years of data from UBDC, Urban Big Data Center. And they are really eager to engage with academics, I want to say, because we also had several conversations with them, and they all know our studies. Sometimes they blog our studies. The problem is the current situation about the safety. So they try to change their data products, and this is because associated with their running their companies, there is some kind of there could be some kind of issue, but in general they are very friendly.
Another question, Jin, can you recommend some resources to study the traffic assignment model?
There are many, actually. There are books and there are papers, but you need to really learn the basic statistical model inside the traffic assignment model. And also you need to run, if you wanna only know the traffic assignment model, you can just use R. There are already code available on the website, online. And also, if you wanna, the easiest way is you use some travel demand models, four-step model software, Transcat or vSim, then you can easily actually do that if you have a data. So yeah, there are a lot of books if you can just Google it, or you can find several books or papers.
And a question about socioeconomic variables is there much, do you use that much, Jin?
No. Again, this is not actually included in the Strava data. They only provide, for example, in the city of Glasgow, they only provide the distribution of the age and gender. So how many females are in that area for that data. So this is very aggregated data. So we could actually use that data to check with the census data and then see who are using the Strava apps. However, we cannot really use that information for the analysis because we don't really know for each trip.
And one perhaps related to the current kind of restrictions, where there seems to have been a bit of an increase, certainly in bike sales anyway. And do you think maybe in these circumstances, it's easier to encourage people to cycle or walk more?
Yeah, I think so. And actually, interestingly, I'm not sure. We are about, yeah, we have a one paper, draft paper that examined the cycling patterns after COVID-19 lockdown in the UK. And then you see we saw a significant increase in terms of cycling activities. And yes, I think that's because of the current situation as well as the new situation, like for bike share program, they provide kind of free ride. And also there are a lot of people who bought the bicycle. So yes, I think so.
And the next one, Jin, what proportion of all cyclists use Strava? Or to put another way, how does your sample size for Strava data compare to the sample sizes for manual count data?
That's great. So again, as I said, I think that's the same for the first question. In our case, it's about 5%. But it varies, city by cities. So that's the reason why I said, one Strava users could represent 25 people, actual cyclists, or sometimes, depending on the city, it could be like 200 actual cyclists. And also it depends on the location, if urban area versus to the rural area, because again, the special variation.
And another one on, could average speed be used to differentiate between the sports cyclists and the commuters maybe?
I think it's easiest one is using the time. If commuter, there are certain time that they are using the cyclists, like AM peak and PM peak. That's better, I think, in terms of separate the commuting trips and non-commuting trips. And in the Strava data, they actually indicate whether they are commuting or not. So if we are using the Strava data, it's easy. If we are using other data sources, it's better to use the time, AM peak and PM peak, to separate the commuting trips. Yeah.
No. Any methods for correcting the self-selection bias inherent in Strava data?
So there are currently several papers. They use some statistical models and use other built environment or other data set and build some model to correct this bias. And there are also some studies using, they are conducting their own survey and ask people whether they are using Strava or not, apps or not, and then their activities patterns. And also they measure the manual counts for different locations. And they use this whole kind of information together to try to correct the bias in the Strava data. So yes, there are papers. It's not simple to understand, but there are people who are working on this issue.
And here's an interesting one from somebody. My own research is in the area of crowdsourcing of qualitative data, the experiences people have whilst traveling. This would be a great addition to the quantitative data, understanding the why as well as the what. Have you worked with anyone in adding that type of data through, for example, a bespoke app?
Currently, for the cycling, no, it was very hard to get the data based on our current situation. So for the cycling, we only have this Strava data. That was the main one. But again, we are trying to purchase some mobile phone data. And then if that is successful, then we could actually use this new data to add new information.
I think as well, Jin, did Catherine's study, did it not ask people to keep a travel diary?
That's the IMCD survey. That's a travel survey, household survey. So that's a little bit different. That's a traditional survey data, and not really the new forms of data like apps, something like that. But we do have in the another data set that we have, Urban Big Data Center, is IMCD survey, which actually Moore just mentioned. There are survey, so it's a representative sample of the whole metropolitan area of the Glasgow. And also some 300 people, they carry the GPS and live logging device for 1 week. So that's another data set we have. We have their travel diary and we have their GPS trajectory and also live logging picture data. So if we may use those kind of data together for the research to get more information.
And actually, Professor Lido, who works on that data, is giving one of the data dives. I think it's next week sometime. It'll be on the website, the details of that, if anybody's particularly interested in that. With regards to cyclist safety, Jin, on the routes, have you looked into how this could be understood, potentially laying crowdsourced data with Stats 19 accident information?
We haven't done it, but we know there are studies, and yes, that's totally possible. We can also look at the in Scotland and UK SIMD. There we know these crime rates of the areas, so we can also see how the relationship between the crime rates and the cycling activities, and also look at the location as the person asked. Yeah.
And just in terms of your work with Glasgow City Council, Jin, are they quite receptive to use this data to help guide their cycling policies and plan infrastructure, for example, new cycling lanes and stuff like that?
They are very supportive. All the infrastructure data they provide us for our own research, and we also provide our research to them. And we are currently under discussion how we can help them to make a better cycling plan. And they are really, really, really amazing people. They are really kind, and they are happy to accept our, happy to collaborate with us.
Yep.
Yes.
I suppose one is. The next one, concern with using Strava data for making planning decisions is it could perpetuate transport inequalities by making women, older, lower income cyclists more invisible.
Yes, that's the one that, so that is a reason why people try to collect the bias actually with by using other data sources. However, as we showed in the study, the general pattern, it's anyway aggregated levels of cycling patterns. And they could give us some kind of good policy implication. And yes, I admit that, yes, it could be the issue.
Now, I might know the answer to this one. Can you track individuals over time? For example, can you see an individual does the same journey every day of the week? Or is it just because of that bin data that's restricted, or can you do it in the older data, Jin?
No, actually, it's not easy because we know for each trip the cycling routes, but that doesn't guarantee that same person has the same ID. They don't have that kind of thing, because yes, if we can do that, that's a very serious privacy issue, and they don't like it, and we also don't like it. So no, I don't think that's easy. That's possible. And especially if you the binned data, I don't think that's possible.
And a question here about, I know UBDC is doing some work on CCTV data for Glasgow City Council. Could you use CCTV data rather than cordon counts as some kind of validation?
Yes, that's what we are trying to do right now. In the CCTV project, we have tried to identify the pedestrian and cyclists based on the CCTV data. If that is successful, I'm pretty sure we will do it, we'll get it. Then we can, yes, compare that data with Strava data and then get the more validation, further validation work. Yes.
And what is the last question for this session? I think how to plan, could you use Strava to perhaps plan the integration of the bicycle as transport in cities where the bicycle use is just emerging? So maybe link back to this kind of COVID restrictions and a lot more increase in people cycling in cities that don't have the infrastructure. Could Strava or something like that be helped to try and...
Yes, I think so, because the first thing that you need to do is you need to understand the cycling patterns, because there is a reason why people use certain roads. But if you can know the whole picture at once in simple way, that will really help you to make a better plans. So yes, so that's another benefit of the Strava apps, because that's available for everywhere in the world. So you can, for example, there are some studies that trying to find out examine the cycling patterns in Africa where there's no really data and no infrastructure. Yes, but I think that's really, so that can be the one potential benefit of this kind of data. You can easily see the cycling patterns, although there could be some bias, but you can easily see what roads are popular and why.
That's great, Jin. Thank you very much. That's all of the questions for this session. Now, I think we're going to have a break before the kind of more practical session. So on my clock, it's 10:55. If we say 11:15, we'll reconvene for the second session. So thanks everyone for taking part. We'll return at 11:15 prompt for the next session. And again, Jin will give a presentation and we can have another Q&A session. So thanks just now.
Thank you.
Hi, folks. Welcome back to everyone. I hope you've all joined us again as we start this second session, which is a more kind of hands-on practical and how to work through some of the examples that Jin talked about in the earlier session. So same as before, questions and answers in the tab, and we'll take them again at the end. So I'll just hand over to Jin again, and thanks for joining us.
Thank you. Thank you for everyone again. And in this session, I will use R and slightly the ArcGIS, ArcMap to show you how to process the data and how the data look like. Again, I'm using R. I don't know how much you know R, but you can just, if you don't have any idea about the R, try to understand the concept. The codes and the data, all data will be available on your request. So if you want to follow the code, my code, please request it through the Urban Big Data Center website. And I hope you can also have a recorded version of this seminar. About the code, there are several ways to build a R code. So I'm not saying that my code is the most efficient one. You can use your own code for the same purpose. So that's something that I want to talk before starting. So I hope you can all see this share my folder and RStudio, right? And this is the data you will get if you request the data from the UBDC, Glasgow 2016, January 1st to December 31st, right edges. That is the cycling data from Strava data. And this is the Glasgow city boundary. Why we need this one, I want to show you the one. So if you look at later, and if you look at the folder, you will see this one. This is the special data. This includes all the special information for all edges, the link, the road segment of the Strava data. And this is the data you will get, whole Strava data with depending on different levels of aggregation. And this one is the hourly aggregation per each link, each edges, for example. So that is what we are going to use. And this is what the data format that you will get it. Then let's look at the data in detail. First, the special data. This is ArcMap. You need a license to use it, but you can download the QGIS for free, and that's very similar. And you can do whatever you the same thing that I'm doing here in QGIS. So if you want to follow my instruction, then you can download the QGIS. And first, so this is the one that I show you, the data folder, and see Glasgow shapefile. You need all this information data set to get the one shapefile. If you click one, you see this one, right? That is the data from Strava. They use some square boundary and they clipped all the edge information and extract the Strava data. But and if you look at this one in the attributes, right click attributes, this is the information that inside this shapefile, the special data, there's ID. So so if I select one link, it will be highlighted. And if I look at the date, the one, its ID is 747718. That is the ID that we need to use to merge Strava actual data with this edge data, right? Because Strava data is Excel file, a CSV or DBA file, and then this is a special location of the edges. So we need to merge them later. There are many information about the edges, the road segments, and here is the kilometers, which is the length of the edges. I want to make sure, because it depends on the maps, but the length of the edges are different. So we may need this information to calculate total cycling distance and the location of the edges. So that is one. Thing is, you may not want to use all data set. You may want to only edges in ACT, right? That's possible. So I download this another data set, which is Glasgow City's council boundary, Glasgow City boundary from the Scotland website. And I think you can get a link from from UBDC about that. We will provide it if you request it. And if you look at this one, this is a city boundary of Glasgow. So I want to only select the edges inside the city boundary for the first purposes. And how can I do that? Here, I use the clip function in analysis. So if I click this one, you see this one, and input features, I put the Strava edge data, right? And then clip features, I put the boundary, city boundary data. And then here, I just define the name of the my final result, Glasgow clip shapefile. You can define the location and then put the name here. So if I click here, okay, then what you got is this data. You see the different color. So I will only show that one. So this is the final result. I only selected the edges inside the city boundary, and it has the exactly same data, right? ID and kilometers and XY coordinates, but I only selected the edges inside the city of Glasgow boundary, okay? And then save as a Glasgow clip. So if I look at my folder again, Glasgow clip, there's all different shapefile information. And in DBF file, that includes the data, like this data, it's a DBF file, the same here, right? So now we know what edges are inside the Glasgow area, right? And then we will use it for the processing to process the data. So I will close this one. That's all I need for ArcMap. So this is RStudio. Everything is free. You can download it. And then if you wanna use the specific function in R, you need to download install the packages and then import the packages. And this is how I import the packages library. I need tidyverse and Lubridate and others to process data. So I run this one here. So first I import all the library. And first in R, I need to tell R where my data are, stored, right? So this is the folder. So in the user, my ID and document and 2020 webinar, Strava and Glasgow Edges, that's the folder where my data are stored. So here, right, this one. So see, this is the path of my folder, and this is the one. So I define in R where my data exists. So I run this one, and now the R know where my data are. And I use the read CSV to import the data. Again, this CSV file is hourly aggregation of the Strava activities. And then I saved it as a Strava, right? I did it. It's very quick. And then let's look at what informations are in the Strava data. So I use the summary function here. And see here, first, there are almost 2 million observations. That's a lot, right? 2 million observations here. And there are 14 variables. What are 14 variables? This is the 14 variables inside the Strava. HID. It's not ID, it's HID. So we need to, if we want to merge this special data with this Strava count data, we use the ID from the shapefile and then also HID from the Strava because they are the same. It has year 2016 and day 1 to 366 because there are 366 days in 2016. Hours 1 to 23, so 1 day, and then minutes. And athlete count is a number of Strava users on their rows on a particular time. And reverse means there are 2 directions on the roads. So they have a 2-direction one. And activity count is a cycling trip, number of cycling trip on that edge. And the reverse is, again, there are 2 directions. And total is the sum of this one and this one for the athlete. And then activities, the sum of activity count and reverse activity count. That's the one. There's a time information, also commuting count. There in the app, you can, after you finish your whole journey, you can indicate whether this is a commuting trip or not. So if they indicate as a commuting, that this is the information about the commuting count. And that is the information we can use to separate commuting and non-commuting trips. Hope this makes sense. And then I will first here, but as I said, this Strava data includes all Strava activity data for all edges, with what we first see. So takes a little bit time. So this one, right? Strava data includes all the edge information, this one. So what I need to only select the edge information, the Strava activity information from edges that are inside the Glasgow boundary. So how can I do that? Here, I read the dbf file. So Glasgow clipped 1 dbf. So that actually gives us all the ID of the edges which are within the Glasgow boundary. Does it make sense? So those are the edges inside the Glasgow boundary. And I only in this, this is the function, this is the command. I use the Glasgow data and then only select the ID and kilometer, the length of the edges, because that's only information that I need from the special data. And I use this data and then inner join, use inner join. What is the inner join? There are different types of join, but inner join means you only keep the data set that matched. So here I joined the data, the Glasgow, the Glasgow clip data ID, and the Strava data, this one, the Excel file, the CSV file, by using ID from the Glasgow file, which is a shapefile, and HID from the Strava data. So I did it, and inner join means only keep the observation that are matched. So I did it. And Glasgow Strava, you see now we have 1.4 million observations because we remove all the counts beyond the edges, beyond the edges beyond the Glasgow City area. Is it clear? Yeah, it's a little bit hard to see your face. I cannot see your face, so it's very hard to see whether you understand or not, but I will keep doing that. We can have a Q&A session later. So now we have all the cycling activity data, Strava data for edges within the Glasgow City boundary. I want to see the travel patterns, cycling patterns, and I also want to check the quality of the data by producing a map. If we produce a map, we can easily see whether the numbers, the data make sense or not. So to do that, first thing, what I did here is I calculate the total count per edges for a whole year. The total annual counts per edges, road segments. Here, I use the Glasgow Strava data. Here, we joined it, right? And the group by ID. The reason is I want to calculate total cycling distance per ID, per edge. So that's the thing. I need to first group them by ID, and then use summarize function to calculate sum of, here I use a total activity count, the total count, number of cyclists, cycling trips, and multiply by the length of the edges. Why? I want to calculate the cycling distance, total cycling distance. And that's all, again, the reason is the edge length of the edges are different. So if we just use the total cycling count, then may be a little bit confusing. So we calculate the sum of this total activity count multiplied by km, kilometers, and then save it as a total distance. And we calculate this total distance by each ID, each edges. So I did it and then save it as a total count. So let's look at the total count. Total count. So edge ID 105, the total cycling distance is 192 kilometers. Or 106, it's 494. So we calculate total annual cycling distance by each edge. Right? That's what I do here. Then I want to show this total distance in a map. Then I can see where are the popular roads, where are the kinds of cycling, where are the cycling activities happen, right? So to do that, I wanna import the shapefile. It can be possible. You can use R to import the shapefile and produce a map in a nice way. To do that, I need these two libraries, ggmet and SF. So I imported it. They are here. Here, I import the Glasgow clip shapefile. What is that? That is, again, takes time to see the ArcMap. This data, Glasgow clip shapefile, this one. I imported it in R by using st_red, underbar red, right? And so I import that data and then use inner join with total count. Total count include the ID and then total cycling distance. This includes all the edge information inside the Glasgow boundary, right? So I merge these two and then save as an edge. So I did it. So now I have edge data. Here, there is 11,000 observation, the edges. And to import the base map, we need to use STBbox and edge, which is the data set that we save. We need to use the same coordinate system with edges. Inside the shapefile, there is information about all the coordinate systems and locations, right? And we need to define the boundary, excuse me. And to define the boundary, we need to use STBbox. So we do that, and if we see what is inside, it gives the 4 values about the boundary. To use the GetMap function, we need to change the name, column name as a left, bottom, right, top. That is a fixed. So if you do that and then see what happened is now it changed, X mean change the left, Y mean change the bottom. So we changed it. This is required if we want to use a GetMap function. And now I want to get the base map and save it as a Glasgow map. So this is what I'm doing. Now I have a base map. You cannot see because I didn't command the print, right? So let's do it here. ggmap is how you print the map. So Glasgow map, the base, I said, oh, print the Glasgow map, base map here. And then data is edges. This is the data. In data, we have all the information of the edges and then total count because we merge them. Total distance, cycling distance. I wanna show the graph, each edges, but the thickness can change, the size can change, depends on the total travel distance, cycling distance, right? So we see if it's thicker, then it means there are high levels of cycling activities. For the color, we use Sienna 1. You can change it to the black, blue, red, whatever you like. Scale size, for the travel total distance, we need to define the breaks for the value. So we use 10, 50, 100, 150. I will show you what it means. And range is 0.1 to 3. You can change it. This defines the thickness of the breaks. Depends on the breaks. And then we put the label. The title is total annual counting distance per edges, and size is kilometers. So let's see what happens if we run this one. You see this nice graph? So I will enlarge the plot. So this is the kilometers, our dependent variable. And this is the breaks. We define it 10, 50, 100, 150, and that has a different size, right? That's what we have here. And we use the Sienna. This is the color called Sienna 1. And that's the graph. We see the river and we see a lot of cycling activities alongside the river and here. As you may remember in the previous session, we have this area, and this area has a really nice cycling infrastructure, good cycling infrastructure, and that totally makes sense. It's not hilly, it's very flat. And see the city center area, there are quite good levels of activities. And then for whole real main roads, there are some activities there. So this shows that, oh yeah, data looks reasonable, and that's what we expected. And that's the easiest way to see the travel pattern in your city, right? So that's what we did here. So if we want to change the key variable, you can change here. It depends on your research. But then now, the whole main analysis that I'm gonna do here is I want to examine the relationship between weather conditions and cycling activities, right? The relationship between weather conditions and cycling activities. So first, I need to calculate total cycling distance, but for different purposes, because commuting cycling distance activities could be different from the non-commuting cycling patterns, right? So we do that. How we do that? And we want to calculate the total cycling distance per day, because if we want to examine the relationship between weather conditions and the cycling activities, we need to make our analysis unit as hourly or daily. But we decide to use the daily here because weather changes by daily. So here I create total cycling data set, but they use the Glasgow Strava data, which is this one, right? All the edge information are there, and also the activity Strava data, raw data. We now group by day because we want to calculate total cycling distance per day. So that's what we are doing here. And we use the summarize function to calculate total activities, means sum of total activity count multiplied by kilometers. So that's a total cycling distance. For the commuting activities, we use commuting count, right? In the Strava data, we see there was commuting count if the users tick the commuting as this trip as a commuting. And then kilometer again, the length of edges. For the non-commuting activities, then how can we calculate? We can use the total activity count minus commuting count. That is the whole non-commuting count, right? Multiplied by kilometers. So then and save as a non-commuting activities. So this total activities means total cycling distance per day, per day, right? So we do that. And let's see what is inside the total cycling data. Total cycling. See, there's a day 1 to 366. It's omitted. It just shows the first 6 rows. And total activities in day 1, there is only 886 kilometers. For commuting, none, because it's a new year, right? No one will work there at the time. And non-commuting, there are some people. So we calculate total cycling distance for commuting and non-commuting by day. Here, later, I want to use nice graph and then plot the date in a proper way. So I use edge date function by using this this variable. So total cycling data, that inside there is a day variable, and we use a -1 because that's how we define the use the edge date to match with this format. So if I run this command, what happened is, let's look at the data again. It has a date. It's a nice format, year, month, and day. So day 1 is the January 1st, day 2 is January 2nd. So that's very easy way to change the format by day from day to date. And here, let's do the sum. So I calculated all the cycling distance, total cycling distance. And then I want to check whether data looks okay. There are many ways, but this is the one way. Just do the summary. And then see, let's look at the total activities, which means total cycling distance by daily. And the mean is 2,500 kilometers for whole area, but max is almost 10 times. That is weird, but that's too large. Then there could be some issue. So here, what I'm doing here is I just wanna see which dates are. So using the total cycling data, and if the total cycling data, the total activity is greater than 23,000, just plot them. That's what it is, what this command means. So we run it, and we have day 255, 255, and that's September 11th. And I Googled it, what happened in Glasgow in September 11th. And there was an annual Glasgow to Edinburgh bike ride event on that day. So that is an exceptional date. And for the analysis, it's better to remove it. So here, I use the total cycling data, the same data, and filtered. So only select if the total activity is less than 23,000. So if I do that, now to the summary again, the max is 10K. You know, it's kind of better, much better, right? You can do more if you are using the Strava data for your cities. You can do more investigation, but I think that's okay for this tutorial. So now I process the data. I check the data, whether there are errors or exceptional days. And then I want to see the trend of the data, because each time series data is 1 to 366. So I want to see the trend of the whole activities. Here, I calculate the moving average. This is a good measure for showing the trend of the data. If we use the raw data, there will be a lot of spikes. So that is very hard to see. But if you use the moving average, it's nicer. Moving average means you average the whole past 7 days and use that average as your value. So I actually find this code from the online. I mean, there are a lot of R codes. You can just Google it if you don't know how to do it. So this is how we make a function to calculate moving average. I will briefly explain here the concept. So this is the new variable that we are going to create, and this is the loop function. So let's assume that the I is the 7th of the January 7th, right? Then the variable, the value will be the mean of activity, which we'll define later as a total travel cycling distance or commuting cycling distance. I minus n. Let's see. We said it's 7, and n equals what? 6. We already predefined it, so it becomes 1, and I becomes 7. So what it means is this function means let's make a mean of activity, your variable 1 to 7. So past 7 days, you use that variables or that values, and then calculate the mean and put the value here, the 7th value of the average variable. Does it make sense? Yeah, that is what I'm doing here. So I create MA function, moving average function. And here, what I'm doing is use this MA function that I create and then use total cycling distance for commuting purposes and non-commuting purposes. This is the variables, and use this function and calculate moving average and save as a MA total, MA commuting, and a non-commuting, right? And use a mutate. Mutate is a function that when I want to make new variables. So I use a total cycling, again, the final data set we use here, processed here, and then save as a total cycling again. So I don't want to make different data set. I want to keep this original one and adding more. So when I do that, see what happened. I just calculate, this command show that, just show me the first 10 observation, and this one. Day 1, total activities, commuting activities, non-commuting activities. That's what we have. And date, that's what we originally have, right? Now there is a new variable, MA total, MA commuting. And I think because the size is so small, it doesn't really produce the other one, but let me do it again. Yeah, so the MA non-commuting. So this is the moving average. So look at here, there is no change until 5th observation, because if you look at this one, if, for example, I equal 5, then this is 5 minus 6, because 6 is predefined, it's minus 1. I cannot really calculate this number. So when it becomes greater than or equal to 0, it calculates the moving average. So this moving average is the average of these 7, 1, 2, 3, 4, 5, 6, actually 6 values. If you average this one, there will be this number. You can check it later. I already did it. So we calculate the moving average, and also we have a raw data, raw cycling, total cycling distance, and total cycling distance for commuting and non-commuting. That's the data we processed. Here, I want to show the trend. I want to make a graph that's showing the trend. So I use the data that we've just processed. One problem is I want to see the whole 3 information, total travel cycling distance for total commuting and non-commuting, and also moving average for total commuting and non-commuting. But that's very hard because the current format has, for example, these three different columns. For you, if you look at the graph plot, the y, there's only one variables, right? So that's very hard. This format, we call it long form, wide form format. To draw the nice graph, you need to transform this wide form to the long form. So how can we do that? It's very confusing, right? Just hold on, I will explain. this is a function that we can change the format. So here, column 2, 3, 2 to 4 means I only use the column 2, total activities, commuting activities, and non-commuting activities, 2, 3, 4. And then use the names to activity type, create new variable, activity type, and put the value as a total distance. This is a new name of the variable, but I only use these 3 columns. So let's see what happened. If I just run this code, now see this one. Now it's the same, but for one day, January 1st, there are 3 rows, and each row has activity time, a type as a total, commuting, and non-commuting. And the total distance here is the value of the original value. 886 here, 0 here, and 886 again here. So I changed the wide format to the long format. So we have one key variable, total distance, and we know activity type, different activity type. Does it make sense? And we use the ggplot to plot the trend. X is the date, 1 to 366, and the Y is the total distance. And then we said, oh, let's print the points, each value, but the shape changed by activity type and the color changed by activity type, because for the activity types, we want to have a different shape and colors, right? And then this is the label. And again, scale bar, the x-axis is a date, and that I want to have this format, year, month, and day. That's a nice format. And GOM line means let's connect all the points by line. So I will show you the final results. That's better to understand for your understanding. So I just use the raw data, not a moving average, and this is what it is. The total activities, it has a blue color and square shape because we define here, right? Different color and different shape. And it has this pattern. The non-commuting green and triangle, and commuting activities red and circle. So we have a different shape for different activity type and also the colors. See kind of seasonality impacts. There are low levels of cycling activities during the winter here, but high activity level during the spring, summer, and autumn. There are some decrease because I think this is because of the holidays. There is no students, not many students here. Also, people are taking their holidays. Again, this is not really easy to see the trend. So I use the moving average. It's the same command, but I use now column 6 to 8 because that's the moving average that we calculate 1, 2, 3, 4, 5, 6. So 6, 7, and 8. Right? And the same thing, exactly same code. So if I do that, you see much nicer trend, right? That is a reason why people use the moving average. You can ignore this part because that's not really moving average. So this is a moving average. You can see the seasonality impacts and also kind of variations depends on because it's weekdays and weekends. Also weather can be the factors why there are such a big variation. Sorry. So now we process the Strava data. We know we have all the total cycling distance for commuting trips and the non-commuting trips by day. So we process data. Now we need the weather data, right? So then we can build a model to see the relationship between weather conditions and the cycling activities. So there are 2 data sets that you can use. One is you can get your data from your local weather stations. That could be more comprehensive. But if you don't have it, you can use these 2 libraries to obtain the weather data for your city. So first, I want to calculate the length of day because, again, the length of day is very important for cycling activities. And in Glasgow, the length of the day changed significantly compared to winter and summer. So I make a sunlight data. First, I define the data frame, the date. We need to ask them what date we need the data and then the location. So I use the total cycling date information that includes the 2016 January 1st to 2016 December 31st, and then put as a date. So that's a data frame. As a in the data frame, there's a date variable which is defined like this one, and we put the latitude and longitude of our city area. How can you do that? If you just Google it, your city, the Google will show you the latitudes and longitudinal information, So you can just type it. That is our data, and we use get sunlight time function to get the sunrise and sunset time. Right? That's what we do here. And we mutate length of day as the difference between the sunset and sunrise. Then we can estimate the length of the day. And we rename date as a date no time, because sometimes date has its own function, so it can be confusing, but it's not really necessary. And then we have a day. We want to have a day like 1 to 366, because it's easy to use for merging other data set by using date no time. Date no time now is January 1st, something like that. So if we do that, and let's look at the data. And date no time is 2016 January 1st, and this format. We have a latitude and longitude information, sunrise information, sunset information. We have length of days, 7 hours. It's been increased, and day 1 to 366. That's what we are doing here. So now we calculate the length of the day for 2016. Now we need to get a more detailed weather data like precipitation, like wind speed and temperature. How can we do that? We can use the getMeta function to get a station information for your cities. So here I also put the latitude and longitude over Glasgow, and then get the metadata. Inside the code, we see different stations. Oh, takes time. Yeah. So these are the stations, weather station in Glasgow. And you can use the code to select the station. Here, we select the Prestwick, the weather station in the Prestwick airport. The reason is it has a list missing value. So we use that code. So we use import NOA function. We define the station, and then we said its year is 2016, and only select date, wind speed, air temperature, precipitation, right? And then mutate date no time again as a date, which means 1 to 366, and that hour of day. That's what we do here. So we only select wind speed, air temperature, and precipitation. And then I look at the weather data Prestwick here. You see, this is the wind speed, air temperature, precipitation, date no time, and hour of day, 0 to 23. Right? That's what we are doing here. So now we have all the weather data, and just want to rather than using the original data set, we want to have a mean temperature, max temperature, and some of the whole precipitation level, and mean wind speed and max wind speed, because that's the more important determinants of the cycling activities. And that's what we do here. So here, if you look at the weather daily, we calculate mean temperature, max temperature based on the original data set. Is it? I think that's straightforward. Then we have a weather condition data and we have length of day data. The next one is we need to merge these two data sets so we can have a full weather condition data. So how can I do that? I have weather daily data, which is the final data set for weather, and sunlight data, which where I calculate the length of the day. And both of the data set has a day, 1 to 666, 366. So we use that variable to merge these two data sets. And now I have a final weather data set, which has all the mean temperature, max temperature, precipitation, mean wind speed, max wind speed, latitudes, longitudes, and length of day. So that is my whole weather data. Now, what I need to do is merge this weather data with cycling data. In total cycling data set, we already calculate this total cycling distance for commuting and non-commuting, and also overall total. We arrange it by day because we wanna put first in we order the data set by day, and then use inner join, same thing. We merge weather data and this Strava data, and then merge them. But before I do that, I wanna make sure we have for the weather data, we have 362 days because there are some missing values, right? So we do that. And then for cycling, we have all the information. We have a total activity, which represents the total cycling distance per day, and the commuting cycling distance and non-commuting cycling distance, right? And all the weather condition data. That's what we have. So that is the final stage. We have all the data processed. Now we want to see the key dependent variable, how they are distributed. So here I plot the key dependent variables, total activities, again, total cycling distance per commuting and non-commuting. They are skewed. That's general, right? So if we want to use some kind of regression model, it's better to make as a normal. So we took here the square root. We take the square root transformation of the key dependent variable and then see how it looks like. Yeah, this one and this one is pretty much better. For the commuting, still it's not really ideal. So you need more investigation if you want to get the if we want to conduct a proper analysis. But for this tutorial, let's just go with it. So here, although this is the time series data, so the observations could be correlated, we assume that they are independent. So let's just run the simple linear, just run the linear regression model, which means that we assume that all observations are independent. And this is the square root of the total activities is our dependent variable. And this is all our weather conditions variables, right? We do that and put the print the result. We see 4 weather conditions have very significant relationship with a level of total activities, cycling distance. So precipitation has a negative relationship. It means if the level of precipitation increases, so more rains, the activity level will decrease. That's what it means. Max temperature increase the level of activities, cycling activities. It makes sense because in Glasgow, max temperature, even in summer, is not really that high. Max wind, if the wind is speed is high, there are fewer cycling activities. That totally makes sense. Length of day, if the length of day increases, the total cycling distance increases, and that also makes sense. These are all consistent with previous studies, right? I want to check the model result. And then see the residual plot from the model to check the model assumptions, because linear regression model, there are several assumptions. And it looks okay, actually. There is not many clear patterns, and then normal QQ plot looks okay. However, again, there could be an autocorrelation issue. And then to test the autocorrelation between observation, we did a Durbin-Watson test. And then see, there are several legs that have a p-value less than 0.05, which means there are autocorrelation issues. If that case, you need to use time series data. So here I used AutoArima function to measure, to use the time series data models. And then to do that, I need a library forecast. And this is the result. You don't have to worry about this other extra coefficient. That's about the time series coefficient. But this one, if you can compare the estimate, this one with the previous one. And what we found is very, very consistent. Although there are some differences in terms of magnitudes, the level of significance and also the signs are very consistent. So we can conclude that, yes, there are significant relationship between weather conditions on and cycling activities, total cycling activities. If you want to examine the commuting cycling distance and non-commuting cycling distance, you can just change this variable, right? And that's the same. I checked the assumption of the time series model, but I still see some of the problem. I don't want to, this is beyond this tutorial, so I don't want to talk about the models, but you, as a researcher, you may want to try other approaches to fix the autocorrelation issues. So sorry for the long tutorial. I think it's a little bit hard to explain without your reactions, but I hope you can get something from my tutorial. Again, this code will be available based on your request. So if you need this code and data, please do apply through the UBDC website. Thank you very much.
And thank you very much for that, Jin. We only have a couple of questions. One of them was about the code, so you've answered that one already. One more question. When you correlate Strava with Cordon, did you use the Strava edges or the Strava nodes, in brackets, intersections?
So we use edge data because the location of the Cordon count, that's not really close to node. It's more likely between the, for example, middle of the edges or something like that. But I think that's the same because the Strava, they record all the people who passed that point. So we use the edge information and correspond to the location of the Cordon count.
That's great. And just one more, which road networks are you working with, which is just the city of Glasgow, I think, is it, Jin?
Yes, that's the location that we use here in the whole the data is Glasgow one. So here, this area. The data you will get for this tutorial is a Glasgow area.
Okay, and just to remind everybody, as Jin has said, and I've posted the links to the data catalog and on the UBDC, which gives information about gaining access to the data. And I've also put the link there for the free GIS software, QGIS, and a link to R, which is also free and open source code. So I'd just like to thank everyone for attending and thank Jin for his presentation and workshop. And the video, the recording of this will be on the UBDC website, but we will need to make sure it's okay for accessibility, given new regulations about accessibility of online content. So once again, thanks very much for coming, and keep an eye on the UBDC. We've got another 3 of these data dives over the next month. So please, if you're interested, sign up and register for these, and hopefully we'll see some of you at these other sessions. So once again, thanks everyone.
Thank you very much. Bye.
Bye.